enabling people with visual impairments to navigate virtual reality with a haptic and auditory cane simulation. Virtual reality experiences today rely primarily on the visual channel to create an immersive experience, which makes them inaccessible for people with visual impairments. We created a novel VR experience by using haptic and audio feedback to enable people with visual impairments to experience the virtual world. Our novel haptic controller simulates the interaction of a white cane to help people who are blind understand and navigate a virtual space using their existing orientation and mobility skills. This haptic controller is paired with an HTC Vive headset used for tracking the user's head position and for delivering 3D spatial audio through headphones. No visual feedback is rendered in front of the user's eyes. Our controller consists of 5 parts: an active braking mechanism anchored on the user's waist, a cane controller that a user holds in their hand, a slider that connects the brake and the controller, a voice coil mounted on the tip of the cane controller to generate vibrotactile sensations, and an HTC Vive tracker on the controller to track the controller's movement. While our cane controller is much shorter than a typical white cane to avoid hitting real obstacles in the room, its virtual counterpart can be as long as needed, typically the length of the user's real cane. When the virtual cane hits on a virtual object, for example, a trash can, the brake stops the controller from moving, generating the illusion that a real object stopped the cane's movement. Meanwhile, the voice coil generates a vibration that simulates the high-frequency vibration when a cane hits a real object. The system also provides corresponding 3D spatial sound to simulate the sound of a real cane hitting on a specific object. With the tactile and audio feedback, a blind user can walk along a virtual wall by continuously sweeping and tapping the wall, which is a standard cane skill called shorelining. Another standard cane technique is called constant contact, which is when a user sweeps the cane controller on the ground. The voice coil generates corresponding vibrations to simulate the texture of the ground. Our controller modulates both amplitude and speed of the audio and vibrotactile feedback based on the user's movements. For example, our controller can render tactile domes on a crosswalk ramp. Here, we also use the brake to provide a short resistance when the tip of the virtual cane sweeps across each bump on the tactile dome to provide the illusion that the cane hits the bump. Users can also tap on different virtual surfaces with the cane controller. Both the voice coil vibrations and the 3D spatial audio are used here to generate the haptics and sounds mimicking the real cane sensations on a specific material. With this technique, a blind user can conduct two-point touch, a standard cane skill used to navigate the environment. Notice that we allow for significant tolerance with the floor penetration, since, though our cane's brake can stop horizontal movement, it cannot stop vertical motion. Since we don't physically limit the user's motion in space, we play a beeping sound to indicate when the user has penetrated the boundary of available space. For example, our system will beep if the cane penetrates too deep into the wall or the floor. To understand the ability of our system to render a virtual space to the visually impaired user, we conducted a usability study with people who are visually impaired. The participants were familiarized with our controller and then asked to explore an indoor and an outdoor scene. Our indoor scene consisted of a room with 4 walls, a carpet, a door, a table, and a trash can. The study showed that 8 out of 9 participants could understand the layout of the virtual room and correctly locate the position of all virtual objects by using the cane controller after only a few minutes of practice using the system.
I found a trash can. I'm tapping. I found a table.
The outdoor scene simulated a street crossing with a sidewalk, a curb with tactile domes, a traffic light, and a busy street with cars going by. Participants were able to identify different parts of the scene, understand the flow of traffic in the street, and were able to cross the street based on the audio signal from the traffic light.
I found the domes at the traffic light. I found the pole with the traffic light button.
Our study provides evidence that our novel virtual reality cane controller enables people who are blind to explore and understand an unfamiliar virtual space. This technology has the potential to enable novel, accessible applications for virtual reality, such as orientation and mobility training.